Okay, so here's where we're at. Well, first of all, I'm going to have an opportunity to actually get some grading done over the next few weeks. That'll be nice. I'll be done with basically, this is my last set of new videos. I can go back to the spring videos starting next week. All right, so today is Wednesday, September 23rd, and we're going to cover lessons 16 and 17. All right, it'll be fun. It's going to be game night tonight. And then remember that the homework for lessons 11 through 18, okay, we just have one more lesson after today, but it's a pretty big one. And we're going to discuss that next Wednesday and go over the answers the following Monday. This homework assignment is due on a Tuesday, which is kind of rare, but it's due on a Tuesday, October 6th. After this, only the final homework is really due on a Tuesday, I think. But the lesson 11 through 18 homework is due Tuesday, October 6th. But don't fall behind. All right. Any questions before we start tonight? Any questions? All right. So let's go ahead and start with the first video.
Hi, everyone. In lesson 15, we talked about discrete probability distributions. Now, in lesson 16, we're going to talk about the expected value of such a distribution. What happens in the long run? So, you may remember this notation here. I hope you do. Mu, this Greek letter represented population mean. But now we're going to talk about the mean of a probability distribution. This is also called the expected value of a probability distribution, denoted by E of x. E of x equals mu. They're interchangeable. The expected value of a probability distribution is the mean of that distribution. Now, the formula for this is given here. And this should remind you of this formula over here from lesson 8. So this formula here was used to compute things like GPAs back in lesson 8. Remember that the numerator up here, the top, summation W times X, that corresponded to a zigzag motion throughout a distribution. And on the bottom, we had the sum of the weights. Okay, so remember back in lesson 8, let's recall this formula. This was a GPA problem back in lesson 8. You should remember these. So remember how we computed GPA. We looked at the number of units. We looked at the corresponding grade. In particular, the grade recoded as grade points. Like, for example, an A minus was a 3.7, and so forth. And we did the zigzag. That's what this summation W times X gave us. We add products. So we wanted, as the numerator, this times this, plus this times this, plus this times this. The weight, the W value, times the X, basically the grade value, we wanted these products, we took these products and we added them together. We added these products. We added the products, W times X. And then we divided by the sum of the weights, that is the total number of units taken by this student, in this case, 12 units, and we computed the GPA. So again, when we computed GPA, we did that zigzag motion, we got the numerator, and we divided by the sum of the weights, the total number of units taken by the student, 12 units here, and we got the GPA. Now over here, when we're talking about this zigzag formula for a probability distribution, what is the sum of the weights? Now the weights are probabilities. Before, weights were given by the numbers of units for the classes, 5, 4, and 3. But now for a probability distribution, the weights are probabilities. And for a probability distribution, what must be true about the sum of the weights? They have to add up to what? They have to add up to 1. So basically, we're taking the zigzag formula from lesson 8. We know that the sum of the probabilities in a probability distribution, well, that has to be 1. So we can ignore the denominator there. And we're basically left with this formula for the expected value or mean of a probability distribution. E of x, or mu, equals summation. The weights are the probabilities. The probability of x times the x value, or you can switch these, summation x times p of x. And again, we divide by the sum of the weights, the sum of the probabilities. We divide by the sum of the probabilities, the weights, the summation p of x. But wait a minute. For a probability distribution, the sum of these probabilities will be 1, and we can ignore all that. We can just take this. All right, now what's the interpretation? The expected value of x, or the mean of the distribution for x, gives the approximate long-run average per repetition. If the random experiment, like rolling a die, for example, the experiment that produces the value of x, if this experiment is repeated many times. So let's say you roll a die 1,000 times, or 10,000 times, or better yet, 1,000,000 times. Then E of x will give the approximate long-run average value for x. This is the result of the law of large numbers. The idea being that the probabilities you see, which are maybe theoretical, idealized, they're the targets. The idea with the law of large numbers is that the observed relative frequencies, for say the die faces, 1, 2, 3, 4, 5, and 6, the observed relative frequencies will observe the theoretical probabilities, namely 1/6 apiece. Right. We're going to see some examples for expected value or mean of a probability distribution next.
Okay, any questions? Any questions?
Hi, everyone. Let's skip straight to example 2, where we roll one die. That random experiment, rolling one die, a standard 6-sided die. Now, if x is the result, the die face we get when we roll a standard 6-sided die, then it turns out that E of x, or mu, the expected value of x, or the mean of this distribution, turns out to be 3.5. And we'll see why. Now, first off, this is the probability distribution table for x. It should look familiar. These are the 6 possible values of x, the integers from 1 to 6, and each of the probabilities is 1/6. The probabilities are all equal. This is called a uniform distribution. These are all equal. Now, because the distribution is uniform, because the probabilities here are all equal, actually E of x is just the straight up average of the die faces. So the naive approach does work. The expected value of x, or mu, is given by the following fraction. We add up the various possible values of x, 1 plus 2 plus 3 plus 4 plus 5 plus 6. And we divide all of that by 6, the number of values. So when you do that, when you take the straight up average of these 6 values over here, the integers from 1 to 6, you end up with 3.5, which makes sense because you look at these integers from 1 through 6, 3.5 seems to be right smack dab in the middle. So it makes sense that the straight average is 3.5. So the expected value of this random variable x, remember, we haven't rolled the die yet. it's a random variable, the expected value of this random variable x, or the mean of this probability distribution for x, is 3.5. Well, so what? So what? I mean, don't you agree that if you roll a die, it could come up a 1, as well as a 2, as well as a 3, as well as a 4, as well as a 5, as well as a 6. What does the 3.5 really tell us? It tells us a long run average. So here's the interpretation. Here is the interpretation of E of x, the expected value of x. The interpretation is that if the die is rolled many times, like let's say 1,000,000 times, you have no life, you take this die, you roll it 1,000,000 times. Maybe you're a total gambling addict. If the die is rolled many times, then the long run average, of the die faces will be about 3.5. So if the die is rolled like 1,000,000 times, then the average of the die faces will be pretty close to 3.5, we would think. So again, here's the idea. Let's say that you really have no life and you roll a die 1,000,000 times. Maybe you get a 1 on the first roll, a 4 on the next roll, a 2 on the next roll, another 2, let's say, a 5, a 3, a 6, and so forth. If you roll this die 1,000,000 times, right? If you take this sum of 1,000,000 die results, and if you divide it by 1,000,000, okay, again, we've rolled this die 1,000,000 times. Roll the die 1,000,000 times. You get these 1,000,000 die results, add them up, divide by 1,000,000, and the result should be very close to 3.5. We'll talk about these issues later on in the course. So that's the idea. The expected value of x, or the mean of the distribution, can be interpreted as a long-run average. The average we would expect if we were to repeat this experiment, in this case, rolling the die, many, many times, like 1,000,000 times.
Okay, on here, I explain why that zigzag formula is consistent with this. It's not that big a deal. But basically, if you do the zigzag rule, the 1/6 factors out. It looks like the classic straight average formula. You can look at it, but it's not such a big deal. We'll talk more about the zigzag later on. I want to get straight now to the deal or no deal problem. Hi,
everyone. Let's go back to example 1, our deal or no deal example.
That's Courtney's board.
Let's say that a deal or no deal contestant has a case. So here is the contestant's case. And here's the contestant next to the case, looking a little nervous, but mostly happy. A little nervous, but mostly happy. And let x be the amount of money in the case. It's a random variable. We don't yet know what the value of x is. However, we know that we're at the point where there are only 3 dollar amounts left in the game. $100, $400,000, and $1 million. The contestant is mostly happy because this is a pretty good game board. So there are only 3 cases left in the game. And you have each of these dollar amounts in each of these 3 cases. One of these cases is held by the contestant. The other 2 cases are up on stage, and we have these models next to them, and they're smiling. All right, so one of these cases has $100 in it. Another one of these cases has $400,000 in it. And the third case has $1 million in it, but we don't know which of these dollar amounts is in which of these three cases. So let's assume that X has a uniform distribution on the three remaining dollar amounts. So each of these three dollar values are equally likely. We would think that, right? We have no reason to think that one value is more likely than any others. Find E of X, the expected value of X, the amount of money that's in the case. In other words, find the mean mu for this distribution and interpret it. So let's find E of X, or the expected value. Now, once again, because we have a uniform distribution, we could just take the straight average of these three values, add them up, and divide by 3. Or we could do the zigzag. Summation P of X times X, or vice versa. You can switch these. So we have the zigzag goes 1/3 times $100 plus 1/3 times $400,000 plus 1/3 times $1 million. When you work that out, you get $466,700. Interpret it. Here's the interpretation. If many contestants, imagine 1 million contestants. If that seems totally preposterous, think 1,000 contestants. If many contestants have the same three dollar amounts in play, namely these three, and we assume a uniform distribution, then the long run average value of the case per contestant is about $466,700. So again, the expected value of X, or the mean of the distribution, this gives the approximate long run average value over many experiments, over many contestants, over many plays. So if you imagine 1,000 contestants in this situation, then on average, the network will be paying out about this much per contestant. That's a lot of money. So generally speaking, the television network will generally want to avoid seeing this case, literally. It'll generally want to avoid seeing this kind of situation because this is very favorable to the contestant.
And the $1 million case, the $1 million case would be the worst case scenario, literally.
The contestant is mostly happy because this is a pretty good game board. It's a very good game board. And the next offer that the contestant gets is likely to be close to this. And then you might ask yourself, would you be willing to take that offer? Or would you like to bet that your case does ultimately have $1 million? Think about that. Different people may have different responses, but would you take the money or would you keep playing? At the risk of having the $1 million revealed at some point. At some point before it's revealed in your case. You're hoping that the $1 million will be revealed in your case. But if the $1 million is revealed in one of these other cases, then that's going to really drop the amount you're going to take home. Next up, what happens if we don't have a uniform distribution? Then you don't want an unweighted average, you want a weighted average. If X does not have a uniform distribution, do not simply take the straight unweighted average. You really are going to need a weighted average, and you really are going to need this formula over here. That's next time.
Okay, now I want to go back to the expected value. The expected value was about $466,000, right? $466,700. Now, what happened? The banker lowballed Courtney a little bit, right? The banker offered $425,000. Courtney countered with $500,000. Okay, that was a bit above expected value, but the banker was risk averse. Okay, because the $1 million case was the worst case scenario for the banker. The banker was, like most of us, risk averse and said, "Okay, you know what, Courtney, I'll give you the $500,000 because I really don't want you to take home the $1 million." All right. By the way, before I forget, do you know who this is? Do you recognize her? Do you know who that is? At number 24, do you know who that is? That's Meghan Markle. Yes, Meghan Markle, the Duchess of Sussex at number 24. Meghan Markle. She's a princess now. All right. How to get that in there. All right. So let's go on. Okay, let's go on to the need for that zigzag. Okay, we are recording. Yep. Okay.
That's a lot of money. We really are going to need this formula over here. That's next time. Hi, everyone. Here's our less glamorous example on computer repairs. An office has 4 computers. We will randomly select a 5-day future work week for the office. Assume no holidays. Let X be the number of computers that need a repair during the week. Here's the probability distribution for X. Now, to find E of X, do you think it would be appropriate for us to take the straight average, add these up, and divide by 5? Is E of X going to be 2? Not necessarily. Why not? Why is it inappropriate to add these up and divide by 5 as our method? Because unlike before, these probabilities are not equal. We do not have a uniform distribution. So we're really going to have to fall back on the zigzag formula over here. Again, you can switch these. E of X or mu equals summation P of X times X or X times P of X. So the zigzag goes this times this plus this times this plus this times this plus this times this plus this times this. Again, you can switch orders, but here's what we get. And we end up with 0.560 computers. You should put the unit here. Here's the interpretation. Over many 5-day work weeks, the long-run average number of computers needing a repair per week is about 0.560 computers. Now, this idea of 0.560 computers, it might not make sense for you for a single week, but remember, we're thinking in terms of a long-run average per week. So, for example, imagine 1,000 5-day work weeks, right? Maybe during the first week, no computers need a repair. In the second week, 3 computers need a repair. In the third week, 1 computer need a repair, and so forth. Take that sum, divide by 1,000, and that average should be about the 0.560. If you had 10,000 weeks or 100,000 weeks, you should get even closer to that, assuming this distribution still applies in 100,000 weeks. Hi, everyone. Let's do a roulette example where we have to come up with the distribution table, unlike in example 1, where it gave the table to you.
By the way, any questions so far? Any questions? All right. The zigzag. Here you got to come up with a table.
Let's figure this out. So let's say that in order to play a round of roulette at a particular casino, you first pay $100. If you bet on red and a red number comes up, that is, if you win, then you win $200. If you bet on red and another color comes up, then you win nothing. Let X, I'll put this in green, let X be your net monetary gain as a result of playing a round in which you bet on red. Find E of X, the expected value, and interpret it. We're assuming that the roulette wheel is typical for America. 18 red slots, 18 black slots, 2 green slots, for 38 slots total. Here are the corresponding probabilities for red, black, and green. So we'd like to fill out a table like this. We want to figure out the distribution table for X. So basically, you either win or lose. And I'd like you to figure out the value of X, what is your net gain if you win versus if you lose, and what is the probability that you win versus if you lose. I'll put the reminders up here. And I'll give you a minute to figure it out. Fill out the table. All right. So if you win, if the roulette wheel comes up red, your favorite color, you're betting on red. If you win, what happens? Well, you win $200, but wait a minute. Remember, you paid out $100 to play the game to start with. So your net gain, the value for X in this case, would be $100. If you lose, what happens if you lose? If you lose, then you win nothing, but you're still out the $100. So your net gain is negative $100, meaning they have a net loss of $100. If your net gain is negative, that means that you've suffered a loss. So that's the X column here. That's the X column here. If you win, your net gain is $100. If you lose, your net loss is $100, meaning that your net gain is negative $100, the value for X. And what are the corresponding probabilities? Well, you win if the roulette wheel comes up red. The probability of that happening is this over here, 9/19, or about 47.4%. Now, what's the probability that you lose? The probability that you lose is going to be 9/19 plus 1/19, because you lose if the roulette wheel comes up black or green. So you lose with probability 10/19. Or about 52.6%. So here is the full table in its full glory. If you win a net gain of $100 with probability 9/19. If you lose, your net gain is negative $100. That is, you have a net loss of $100 with probability 10/19. Here's the table cleaned up. To find the expected value of X, it's the zigzag. It's this times this plus this times this. The zigzag. So E of X, or mu, is 9/19 times $100 plus 10/19 times negative $100. That's negative $5.26. The interpretation: if you play many rounds of roulette, think 1,000 rounds. I hope you're not that much of a gambling addict, but if you play 1,000 rounds of roulette at this casino and you always bet on red, you love red, your long run average net loss will be about $5.26 per round. Now, it's good to interpret what a negative sign means. So you either want to say that your long run average net gain is negative $5.26, but since we don't like to use negative signs in our interpretations, we like to interpret what the negative sign is. So you should say that your long run average net loss will be about positive $5.26 per round. But it's either one or the other. Your net gain is negative or your net loss is positive. It's one or the other. Don't do both. Don't say your net loss is negative. That's a double negative. All right. Interpret negative expected values appropriately. Now, the reason why, if you play many, many rounds of roulette, you get this as your long run net average is because of the law of large numbers, which say that the probabilities that are built into the game will crystallize in the long run. So in other words, the observed relative frequencies of red, black, and green will approach the corresponding theoretical probabilities, the probabilities that we had listed way up here. In the long run, the observed relative frequencies of red, black, and green will approach these theoretical probabilities, 9/19, and 1/19. And because of that, we expect this long run expected value to represent your long run expected average in the long run as the number of rounds approaches infinity. Now, because the probabilities will crystallize in the long run, and because this payoff structure actually works against you. Because remember, a fair payoff would allow you to win a bit more than $100 if the expected value is truly to be $0. For a fair game, by definition, for a fair game, that is a fair payoff, the expected value of X should be $0. That means no harm, no foul. That means that in the long run, you don't expect either the casino or the player to make a gain. But of course, casinos are in it to make money. So if E of X is the expected value of X, where X is the net gain to the player, right? Then E of X will typically be negative if you're playing a casino game. In order for E of X to be 0, this would have to be a bit more than $100. Think about it. If you had to make a lot of money, how do you maximize your chances of winning a huge amount of money? My suggestion would be put it all in one shot and hope. Because in the long run, the law of large numbers will kick you because the payoff structure is set up so that E of X is negative. If E of X is negative, this is not a game you should be playing in the long run. You should not be playing casino games in the long run. You should not be a gambling addict because the payoff structure forces E of X to be negative, where X is the player's gain. So in the long run, casino games hurt you financially. That's the key lesson here.
Absolutely. That's a key lesson. All right, folks. Let's pause this. I got a couple things to show you. Okay, well, I'm going to talk about variance and standard deviation, but don't worry too much about that right now.
Hi, everyone. I have optional written notes about the variance and standard deviation of X. Here's the bottom line. Basically, the standard deviation of X tells us how useful the expected value is. Like in gambling, let's say that X is your net gain monetarily from a game. If E of X is negative $10, so the expected long run loss is $10 per game. If the standard deviation of X is big, like $1,000, there's a huge spread. So if you play the game a bunch of times, then it's quite possible that you could win a lot of money or lose a lot of money. The possibilities really vary. Now, if E of X is negative $10, once again, but if the standard deviation of X is, let's say, $0, what does that mean? That means the game is possibly rigged. This means that you will certainly lose $10 per game. Every time you play the game, you lose $10. You lose $10. You lose $10. There's no variation whatsoever. So the standard deviation of X tells you how useful E of X is. Hi, everyone. Lesson 17 is on counting, which is the basis for many probability problems. Counting. It's not quite as easy as it sounds, but we are going to count how many possible ways that things can happen. In part A, we talk about the fundamental counting rule, which drives much of this lesson. Let's say there are two decisions to be made, decision A and decision B. For example, let's say there are M possible choices for decision A. Let's say there are 3 possible shirt colors you can choose from. Let's say that there are N possible choices for decision B, regardless of how A is decided. So let's say that you have 5 choices of hat color. And let's say that your choice of hat color has nothing to do with your choice of shirt color. You don't care about fashion. Then there are M times N possible ways to decide both A and B. You have a total of 3 times 5 or 15 possible ways to choose a shirt color and a hat color. If you have more than 3 decisions to make, then you just multiply the corresponding numbers of choices. Now, it could be you who's making the decision, or it could be fate. So, in example 1, we're going to look at passwords. Assume that a password must have the following characteristics. We're going to find out how many possible passwords there are, how many valid passwords there are given these specifications. So the password must be exactly 4 characters long. It must begin with an uppercase letter that affects the first character, and each of the other characters can be an uppercase letter or a digit from 0 to 9. That affects these other 3 positions. Well, we can think of a big bushy possibility tree here. How many possibilities are there for the first character? Well, how many possible uppercase letters are there? There are 26 in the English language. Now, for these other 3 positions, regardless of what happens here, how many possibilities are there for an uppercase letter or a digit? Well, there are 26 uppercase letters. There are 10 digits from 0 to 9. So we have a total of 36 possible characters for the second position, regardless of what happens in the other positions. For the third character, again, we have 36 possibilities, regardless of what happens elsewhere. For the fourth character, again, we have 36 possibilities, regardless of what happens elsewhere. Again, think of a big bushy tree with many branches. The total number of possibilities, the total number of 4-character passwords that are valid here will be 26 times 36 times 36 times 36, or about 1.2 million. What's a faster way of writing this? 26 times 36, what? 26 times 36 to the third. Very often we can use exponents or powers to write this as shorthand, to show work, and you should show some work. If you give me a final answer that's wrong, how can I give you partial credit? Remember that on a calculator, the exponentiation should precede the multiplication. So 36 to the third comes first, and then you multiply by the 26. Okay, now this leads directly to a probability problem. Let's say that all possible passwords are equally likely, and you get a random one. We're assuming a uniform distribution among these 1.2 million plus passwords. What then is the probability that your randomly selected password will be I hate you? I-H-8-U. What's the probability you get that by chance? Well, each of these are equally likely. The probability of you getting this or any valid password will be 1 over the 1.2 million or so. So that's why these counting problems can lead directly to probability problems.
All right. So low probabilities. Let's talk about that.
Hi, everyone. It's the Olympics. Let's say that A, B, and C run in a race. Find the number of possible orders of finish, assuming no ties. So, in particular, how many ways are there for fate to assign a gold medal, that is for first place, a silver medal, that is for second place, and a bronze medal, that is for third place? How many ways can fate assign these medals to the 3 runners? Well, how many possibilities are there for the gold medal winner? The gold medal winner could be A, B, or C. There are 3 possibilities. Regardless of who comes in first and wins the gold, how many possibilities are there for second place? Well, regardless of who wins, there are 2 possibilities for second place. And then, once we know the first 2 winners, we know that the bronze winner is forced. It's the last person. Here, everyone gets a medal. Here's a possibility tree. There are 3 possibilities for first place. And regardless of who comes in first, there are 2 possibilities for second place. And regardless of who comes in first and second, third place is forced. It's the remaining person. So how many possible full permutations or orderings are there for these 3 runners? How many possible sequences are there where we cannot repeat? Well, we have ABC, ACB, and so forth. There are 6 possible paths here, corresponding to 6 possible sequences or full permutations, where we order all 3 runners. How can we calculate that there are 6 possible sequences, 6 possible full permutations? Well, again, there were 3 possibilities for first place or gold. There were 2 possibilities for second place or silver. And there was 1 possibility for bronze once we knew the first 2. So 3 times 2 times 1 is 6. There's a name for 3 times 2 times 1. From your algebra class, this is 3, what's that? That's 3 factorial. 3 factorial. It's not yelling the number 3. It's 3 factorial. We take the integers from 3 down to 1 and we multiply them together. 3 factorial is 6. Let's say that you have a deck of 52 cards. How many ways are there to order a deck of 52 cards? We're looking for the number of full permutations from the first card to the last card. Well, how many possibilities are there for the first card? There are 52 possibilities. Whatever that first card is, leave that card out. How many possibilities are left for the second card? 51. This is like the ace, king, king problem, sort of. Keep on going, and then at the very end, the final card is forced. So the number of full permutations of the 52 card deck of cards is 52 times 51 times da-da-da times 1, also known as 52 what? 52 factorial. 52 times 51 times 50 times da-da-da times 2 times 1. We get 52 factorial. On your calculator, you should see an n factorial button, or if you have a TI calculator, it might be in the PRB menu. What is 52 factorial? It's very large. You need scientific notation. It's about 8 times 10 to the 67th. In fact, it's a bit more than 8 followed by 67 digits, like 67 zeros. This is literally astronomical. In fact, if you consider the number of seconds since the Big Bang, when the universe began, you would think that's huge. It's literally astronomical. But it's only about 4 times 10 to the 17th, about a 4 with 17 digits after it. This number here dwarfs this number over here. This is way bigger than this number over here. Now, what is the total number of atoms in the universe? That's more like 10 to the 80th. This is more in this ballpark over here. We're talking about literally astronomical numbers.
Okay, any questions so far? Any questions so far? All right, these are big numbers.
Hi, everyone. Let's talk about n factorial. Again, on a TI calculator, you can find this in your PRB menu, the probability menu. So n factorial is the product of all the integers from 1 up to n. Or if you want to think of a countdown from n down to 1. We can interpret n factorial as the number of ways to order n different items, or it's the number of full permutations of n distinct items, like, for example, a deck of 52 cards. On calculators, you should be able to find that n factorial button, or go to the PRB menu. Now, for 0 factorial, ignore this. We just defined 0 factorial to be 1. That helps make our formulas work later on. 1 factorial is just 1. 2 factorial is 1 times 2, or 2 times 1, with the countdown approach. 2 factorial is 2. 3 factorial is 1 times 2 times 3, or it's 1 times 2 times 3, or, using the countdown approach, 3 times 2 times 1, which is 6. That's why we had 6 possible ways to assign gold, silver, and bronze to the 3 runners. Now for 4 factorial, we could think of it as 4 times 3 times 2 times 1 is 24, but we can also think of 4 factorial as 4 times 3 factorial. 6 times 4 is 24. In fact, the way to get the new factorial is that you multiply in the new integer. So notice that from 2 factorial, if you multiply in 3, you get 3 factorial. From 3 factorial, if you multiply in a 4, you get 4 factorial, and so forth. This is called a recursive relationship for factorial. Multiply 4 factorial by 5, 24 times 5 is 120, which is pretty big. If you have 5 runners in a race and they get gold, silver, bronze, tin, and dirt, there are 120 ways to assign the medals, and so forth. Notice that n factorial grows very rapidly. In fact, 15 factorial is already over a trillion, 10 to the 12th. N factorial grows rapidly. In fact, in the long run, it grows faster than any exponential, like 2 to the n or 3 to the n. Here, we're multiplying in bigger and bigger numbers. N factorial grows rapidly. And we're going to use this thing in many of our formulas.
Any questions? You may have seen this in your algebra class at the very end. Any questions? Let's look at some more counting problems.
Hi, everyone. Try to have your calculator work this out. What is 100 factorial? The number of full permutations or orderings of 100 different or distinct items. Your calculator blows up, doesn't it? This is way too big. So that's the number of full permutations of 100 distinct items. Now that's fair for homework. These n factorial problems are fair for your homework. But partial permutations will not be fair on your homework. Now, these correspond to NPR on your calculators. Again, NPN, the number of full permutations of n distinct items, which is n factorial, that's fair. But these will not be fair, where r is less than n. So for example, let's say that we have 7 runners running in an Olympic race. Again, no ties. In how many ways can fate assign a gold medal for first place, a silver medal for second place, and a bronze medal for third place? So in other words, what is 7p3? The number of partial permutations of 7 distinct items taken 3 at a time. So we have a pool of n equals 7 runners. Of these, we have r equals 3 medalists. And the order matters among the medalists. Oh yes, you care if you win gold versus bronze. Lawsuits have been brought. We want 7p3. Well, how many possibilities are there for the gold medalist? 7. How many possibilities are there then for the silver medalist? Then we have 6 possibilities. Once these 2 have been established, how many possibilities for the bronze medalist? 5. So 7 times 6 times 5, this is really based on the old counting rule, and that's 210. Or another way to look at it, if you consider all 7 factorial ways to order all 7 runners, there's a dividing line. Line them up in order. We care about the order among the 3 winners, but we don't care about the order among the 4 losers. Now, I know that it's cruel to call these losers, but in China, you better win the gold, otherwise you're a loser. Certainly in China, the non-medalists would be losers. But since we don't care about the order among the losers, we take the 7 factorial and we divide it by 4 factorial. And that's how you get 7p3. When you do this, and you do these cancellations here, you end up with 210. 7 factorial is 7 times 6 times 5 times. The rest of this is 4 factorial. That cancels out with the bottom. So again, 7p3 is the number of ways to choose and order 3 different items from a pool of 7 different items without replacement. You can't have one person getting 2 medals. It's the number of partial permutations of 7 distinct items taken 3 at a time. The general formula goes like this. NPR, where R is no more than n, integer, it's equal to n factorial, the number of full permutations of the n runners, divided by n minus r, all factorial. If there are r winners, there are n minus r losers, and we don't care about their order. Now, next up, what if we don't care about the order among the winners either?
Okay, now, again, we won't have NPR problems on the homework. NPN is n factorial, that's fair. But I just wanted to set you up for combinations next.
Next time. Hi, everyone. Next to the NPR button, you should see the NCR button, which is combinations. For example, let's say we have 7 runners in an Olympic race, no ties. And let's say that there are 3 gold medals for the 3 winners. And the runners don't care which of these 3 medals they get, they just want a gold medal. A medal is a medal. Find the number of ways to choose 3 winners among the 7 runners. The number of ways for fate to assign the 3 gold medals to the 7 runners. So we have a pool of n equals 7 distinct runners, no clones. And from here, we're going to draw r equals 3 winners, the gold medalists. But this time, unlike before with NPR, this time with NCR combinations, the order among the winners will be irrelevant. They don't care which gold medal they get. So we take the 7 runners. Imagine that this is their order of finish. 7 factorial is the number of ways to order all 7 runners. Just like before, we don't care about the order among the 4 losers, so we divide by 4 factorial. But this time, we don't care about the order among the 3 winners either. So we also divide by 3 factorial. All these 3 runners get a gold medal. They don't care which one. So that's the formula for 7C3, or 7 choose 3. The number of combinations of 7 distinct items taken 3 at a time. How many ways are there for fate to choose 3 runners, 3 winners, 3 gold medalists out of the 7 runners? So 7C3 is 7 factorial divided by the 3 factorial and also the 4 factorial, because we don't care about the order among the winners or among the losers. 7 factorial is 7 times 6 times 5 times 4 factorial, which cancels out with a thing down here. Okay. 3 factorial is 6. When you work this out, you get 35. On a calculator, remember that's a double division. You're dividing 7 factorial by both 3 factorial and 4 factorial. Or if you find the NCR button on your calculator, it might be in the PRB menu on the TI calculators. You might press in 7 NCR 3 equals or enter, and you'll get the 35. There are 35 ways for fate to choose 3 gold medalists among the 7 runners. In general, here's the formula for reasonable integer values of n and r. NCR, or n choose r, equals n factorial, the number of full permutations of all n runners. You divide by r factorial, where r is the number of winners, and you also divide by n minus r, all factorial, where n minus r is the number of losers. Here's another way to look at it. Let's say that you assign the numbers 1 through 7 to the 7 runners. These are called the bib numbers, the numbers that runners have on their backs before the race. They're assigned. After the race, you take a photo. Here's runner number 1 all the way through runner number 7. And we're being kind of rude. We're putting a big L on the runners who have lost and a big W on the runners who have won, the medals. Here's another way of looking at 7C3. 7 choose 3. It's the number of ways of ordering or permuting this word, this fake word, WWWLLLL. How many ways are there to order this word? We take 7 factorial, We don't care about the order among the W's, so we divide by 3 factorial. We don't care about the order among the L's, so we divide by 4 factorial. Again, the answer is 35. That's another way of looking at this problem. Here are some related questions, which also lead to 7C3, or 35. Let's say you're given a list of 7 essay questions in an English class, and you must choose 3 of them to write on. And it doesn't matter what order you write them in. How many ways are there to choose the 3 questions? Well, 7 choose 3, or 7C3, which is 35. Also, let's say that you have a test consisting of 7 questions, and you answer all of them. You're told that you got 3 of the 7 correct. You got exactly 3 questions right on the test of 7 questions. How many ways were there to get 3 questions right out of 7? The answer is 35. It could have been the first 3 questions you got right. It could have been the last 3. It could have been 1, 2, and 4. There are 35 possible triples. Here's a pre-virus question that's related. You have a Halloween bowl with 7 different candies. What's your favorite candy? What, Snickers, Three Musketeers? You have 7 candies, different candies, in this Halloween bowl. A spooky skeleton comes to your door. How many ways are there to give the skeleton 3 candies out of the 7? Order doesn't matter. The skeleton just cares which 3 candies it gets. Well, 7 choose 3, or 7C3, that's 35. 35 ways to give 3 candies out of the 7 in the bowl. So these are very useful problems. In poker, let's say you're dealt a 5-card hand. The King of Hearts, the Queen of Hearts, the Jack of Hearts, the 10 of Hearts, and the Ace of Hearts. Are you mad that these cards are out of order? No. How should you feel, actually? If you go to a video poker machine in Vegas, you should feel thrilled, because this is called a royal flush. Technically, the Ace of Hearts looks better over here, but the order among the chosen cards doesn't matter. You always have the right to reorder the cards in your hand. That's my idea of a hand. All right, we draw 5 cards from a 52-card deck without replacement. Of course, we're not allowed to copy cards. Find the number of possible 5-card hands. How many ways are there to get 5 cards out of this deck of 52 without replacement? Well, it's 52C5 or 52 choose 5. Hopefully, you can do this on your calculator, but if you have to work it out, 52 factorial is 52 times 51 times 50 times 49 times 48 times 47 factorial. That covers 47 down to 1. And that cancels out with the 47 factorial in the bottom, because we don't care about the 47 cards left in the deck. Likewise, we don't care about the 5 cards in your hand, so we also divide by 5 factorial. We get about 2.6 million.
The order.
So, by chance, what is the probability that you get this Hearts Royal Flush by chance? It's going to be 1 over this. In fact, the probability of getting any particular card, any particular hand of 5 different cards among the 52 cards, where the order is irrelevant, is going to be 1 over about 2.6 million.
All right, any questions? Any questions?
Hi, everyone. By the way, you're a bit less likely than 50% to get a pair or better versus nothing at all. Anyway, the hard part about this lesson is not the calculations or showing work. There's not much work to show. Over here, 52C5 or 52 choose 5 equals this number. You don't have to show this work over here. The problem is not the showing of work, it's knowing what rule you use. So here's a schematic to help out. A couple of key questions. First of all, are possibilities being reduced for future tasks or decisions. If not, then the fundamental counting rule may apply. That's like the passwords problem. As you were looking at the characters in the password, you were allowed to repeat characters, for example. In principle, your password could be AAAA, although I wouldn't recommend that. That's like Spaceballs, 1, 2, 3, 4, the movie. All right. Now, if possibilities are being reduced, then we have to ask, does the order matter among the chosen or winning items? Now, it may not be order. It might be color or something like that. But order or something like that, does it matter? If order does matter, like in the runner's problem, then you have a P or a factorial problem. Remember, NPN is n factorial. A factorial problem is really a P problem, where order matters among the winners. In n factorial, everyone wins a medal. Now, if the order doesn't matter among the chosen or winning items, like with the Hearts Royal Flush up here, if the order doesn't matter because you're allowed to reorder the cards in your hand, then you have a C problem, like in the card or poker hands problem. So the hard part is knowing what to apply, just straight up multiplying, or you could have exponents, for example. Or you have a situation where possibilities are being reduced, and then you have to wonder whether order matters or not among the chosen items.
All right. So if you really like the stuff, all right, the math behind the greed game.
Hi, everyone. In the game show Greed, when Daniel was going for the $2.2 million, he was given a game board with 9 options. 4 of them were correct. And Daniel had to get 4 out of 4 right. Daniel had to pick 4, and all 4 had to be the 4 correct options. The order was irrelevant. He could have picked them in any order. But how many ways could Daniel pick a group of 4 options from this game board of 9? For example, if Daniel threw darts, how many ways could he pick 4 out of the 9 options? 9C4, or 9 choose 4, or 126. There were 126 ways that Daniel could pick a group of 4 options from this game board of 9 options. So given that only one group of 4 options is correct, what is the probability that just by random chance, or if Daniel knew nothing whatsoever about odors, what was the probability that Daniel would win this game? What is his prior probability? It's 1 over 9 choose 4, or 1 over 126. This is less than 1%. That's the prior probability. Now, the question that Daniel should have asked himself was, how much did his knowledge of odors improve on the 1%? But remember, from our medical diagnosis problem, our cooties problem, it's really, really hard to raise a prior probability of 1%. And maybe Daniel should have thought about that before he gave up the $200,000 and went for the $2.2 million. Did he know enough about odors? Apparently not. You have to know statistics.
Yeah, I guess the NBC or whatever, they knew their statistics, right? All right. I might talk about this guy later. I already put up the video. Okay, so thank you for staying. Yeah, that was I had a blast doing that. All right. Starting next week, I'm going to go back to the spring videos. They're so good. They're my early videos. I was still fumbling, but they were good videos. I'll stick around for questions. All right. We're still recording, but any questions right now? Any questions? That's lessons 16 and 17. We have 18 coming up on Monday. That's the last lesson in this block. All right. I will now stop the recording.